Hello everyone. Welcome to another informative and career deepening webinar at this complete machine learning externship by Hamoye. I am Gaurav Jain, Junior Data Scientist at Hamoye AI Labs, and I would like to welcome you all and congratulate you all in taking this bold and impressionable step to join this webinar today. Each of us want to become a complete machine learning expert by the end of this externship, and at Hamoye, we are working to help you achieve this goal. In that light, today we have a colossus of machine learning and data science, one whose mentorship helped hundreds of people to become expert in data science, machine learning, big data, data engineering, etc. Mr. Wale Akinfaderin. Mr. Wale Akinfaderin, who is machine learning engineer at Amazon Web Services. He'll be helping us through a Q&A session today. Before we continue, a few housekeeping rules. This webinar will last for an hour. And to ask questions, you can use slido.com with event code hashtag 70189, and they will be promptly answered by a resource person. You can also use the chat boxes in Zoom to actively participate in this webinar and make your contributions. In case you must speak, please raise your hand and you will be unmuted. So keeping your excitement high, I would like to invite Sophia Jack, Junior Data Scientist at Hamoye, to lead you through this webinar. Enjoy the rest of the webinar.
Thank you, Gaurav. I'll begin by introducing our resource person to you, Wale Akinfaderin. Adewale Akinfaderin is a data scientist at Amazon. He has expertise in machine learning, deep learning, statistical experimentation, and general information theory. He has broad experience in implementing and extending ML techniques to solve practical and business problems. In the past, Wale has built data veracity models using machine learning and natural language processing techniques for international development, and also developed machine learning algorithms to solve problems in the renewable space. He's an advocate of open source and democratizing learning. And also his writings on data science and machine learning have been featured on platforms such as Hacker News, Data Science Central, Data Science Nigeria, Data Economy, R Bloggers, and IBM DSX. Wale has presented in technical conferences like the ML for All conference in Portland and the Google Developers Machine Learning Summit. He also advises startups in the data science and artificial intelligence space. It's quite an honor to have you here with us, Wale. Thank you for joining us. So in this session, Wale will be providing answers to questions bordering on Python for machine learning, regression, and classification in machine learning, and other related areas that will help you reach your goal of machine learning proficiency, like Gaurav mentioned. Some questions have already been curated, and I'll be reading them out to Wale, after which any of us that have questions can use the chat box or Slido, or you may even be allowed to speak. Just put up your hands. I'm sure you have lots of questions on these topics. Please type in your questions in the chat box on Zoom or on Slido using the event code 70189. 70189. And Wale will give you the answers you need. So we start with the first question on our list. I am an absolute beginner in machine learning, and I'd like to know the essence of algorithms and how I can choose the best possible algorithm in order to solve a problem. I'll take it again. I'm an absolute beginner in machine learning, and I'd like to know the essence of the algorithm and how I can choose the best possible algorithm in order to solve a problem. Wale.
Yeah, okay. Thanks for the introduction. Thank you guys for having me. Happy New Year to everyone. I'll start with the first question. An absolute beginner in machine learning, and what's the essence of machine learning algorithms? The idea around machine learning algorithms in a short form is that you have data, and then you want to iteratively learn from the data. And you also want to actually make sense of the data. That's why you have machine learning algorithms. So just think about people that forecast weather, right? There are a lot of factors that they look at. They actually, in some cases, they look at historical data. They look at what happened last year, what happened a few years ago, and just a few other things. And then they try, even without using machine learning, they try to infer from those historical events to actually predict the future. So that's in summary what I would say. It's the essence of machine learning is that you have so many data, and then you actually want to find a way to learn from those data, and in some cases you want to predict the future. So machine learning has different types. Sometimes people just summarize it into maybe 3 or 4 types. So there's the supervised learning. So the supervised learning is, I think there's a question about that. Is you having labels and you actually want to predict these labels. Unsupervised learning is like you shooting in the dark where you don't have labels, but you want to find a way to sort of understand your data set and group them using some sort of methods. And then there's the reinforcement learning, where you sort of have an action, you have an environment, and you give this action rewards, and every time you give it rewards, it tries to adapt to the environment and it moves. The reinforcement learning is mostly used. I've seen people use it in sort of the robotics. Some people are trying to adapt it in sort of self-driving cars. Um, so yeah, the essence of algorithms is to learn from data. And then how can you choose the best possible algorithm to solve a problem? So there's a theorem that came out in 97, which is called the no free lunch theorem. And the idea of the no free lunch theorem is that you really, if you have two algorithms, they would probably perform the same on the same problem, given that you're looking at different metrics. So choosing the best algorithm depends on your own heuristics. It depends on the factors that you're looking at and what you exactly want to take out of the project. So I cannot. So the reason why I said so is that let's think about it. Maybe you're trying to choose an algorithm, but you want the one that is faster. You have algorithm A, B, and C. Maybe C is faster, but you want it to be faster, and also you want probably a very good predictive performance from the algorithm. So what that means also is that maybe the one that is much more faster has poor predictive performance. So which means you have to go to another algorithm. Now, let's say you want your model to be explainable. Maybe the ones that is the algorithm that has good predictive performance and faster, both of them they don't have like good explainability, right? Then you go to algorithm A, right? So the best way to choose the algorithm actually depends on the problem you want to solve. Are you trying to scale? Are you looking for computational speed? Are you looking for predictive performance? Are you looking for sort of explainability or interpretability of your model? What are the thresholds that you're looking for? So the no free lunch theorem means that no single algorithm can solve all your problems. So there are basically no best algorithms. There are heuristics and there are also sort of guide. In simple terms, if you're choosing supervised learning because it has labels, there are a bunch of algorithms that you can use. Logistic regression, linear regression, random forest, decision trees, and all that. If you're choosing unsupervised, there are a bunch of other models. So yeah, according to the type of problems, that works. But even after that, you're still left with a bunch of groups of machine learning algorithms that you need to choose from. So I would just say, yeah, no free lunch theorem. Define your heuristics, what are your goals, and that would help you choose the best machine learning model.
All right, thank you.
Yeah.
You made mention of linear regression and logistic regression as algorithms. Can you Explain the difference between the two, and can you give us a use case of linear and logistic regression?
Y- Yeah, I mean, yeah. So linear regression and logistic regression, they're both families of the linear models. So linear regression is used for regression problem, which regression problem means that your target variable is actually the continuous values. So let's say, for example, you want to predict, which nobody does, right? You want to predict stock market tomorrow. You want to predict sort of what the price of a stock is going to be, or what the price of multiple stocks are going to be. But you want to predict house prices in Lagos based on historical events. That's You can actually use a linear regression. So you have sort of your targets, and also so some people call it dependent and independent variables. And you have your features. So you have your features and your targets. And your targets in this case is actually the house prices, for example, that you're trying to predict. There's some assumptions the linear regression do have, which is it's a lot. If you have main features, one of it is that you want to make sure that they don't have sort of strong correlations between the features. Maybe if the correlation coefficient is above 0.8 or 0.9, that might be a red flag. You also sort of want to make sure that your sort of errors are multinomial. And then there are sort of some other sort of conditions or other properties that logistic linear regression should have. Yeah. But like I mentioned, the output is continuous. And the way there's this really nice way where you can go back to, if you've done statistics and you've done maybe maximum likelihood and probability distribution, that you could actually take your normal distribution and sort of your maximum likelihood estimation and use that to derive what they call the cost function. So the cost function is the mean squared error for the logistic regression. I mean, there are other ones, which the mean squared error is a p-norm of 2. So there's other ones like the mean absolute errors and things like that. But for logistic, that's a linear regression. For logistic regression, it's a little bit different, especially now you're actually dealing with classification problems. So if you instead of you predicting the price of houses, maybe you'll predict if this house is good or bad based on the properties. So the properties could be what, or the features could be what area is the house located, how long has it been, how clean is it, what's the price, just different factors. And you want to just say, is this a good buy or not a good buy, for example. So now you're dealing with a binary classification problem. For those who have done statistics, in this case where you're dealing with a binary classification problem, so yes or no, that's going to be a Bernoulli distribution. So you have a Bernoulli trial. And then in some cases you have multiple yes or no, right? So you still have like a conglomerate of Bernoulli trial. And you could also use that to derive what they call the cost function. So the cost function, like I mentioned, for the linear regression is mean squared error. Then for the logistic regression is called the cross entropy loss. That's the cost function that I use for logistic regression. So logistic, even though they call it logistic regression, it is for classification, and the linear regression is for regression. And both of them, they're extremely powerful methods, even though they don't have good predictive performance like the others, but they still have very good interpretability. So the idea of interpretability, explainability, is that you want to explain every decision that your model is making. So if your model predicts that this house is not good, for example, They actually give you, for each prediction, you could see the coefficients of, or the weights of each feature. And that will tell you, oh, my model is actually shows this prediction because it's giving more weight to the size of the house, or it's giving more weight to the location of the house, or more weight to the number of rooms that the house has, and things like that. So they're pretty straightforward. Sometimes more computationally, less computationally expensive, but also the predictive power are interpretable.
Thank you for that clarification.
Okay.
So if I were asked to build a classification model, how do I know the best classifier model to use?
All right. This is just similar to the first question, where I mentioned that there's no free lunch. I can tell you what my approach is. So for classification, I mean, these are the models you can use for classification, and they're not exhaustive. I can explain. So you have logistic regression, you have naive Bayes, um, you have a KNN classifier. So what I do is those three methods, and SVM, support vector machine, those four methods that I mentioned, I classify them as non-tree classifier. So they're not based on you trying to build a tree. So which is logistic regression is a linear model. Naive Bayes is sort of probabilistic model with some properties from the Bayes theorem. And then there's sort of KNN classifier, which sort of use a nearest neighbor algorithm to classify your data set. And then I think the last one is the support vector machines, which is a sort of a little bit different from the other three. Right? So those are non-tree based. And then there are tree-based classifiers. And these are classifiers based on you sort of building trees and going from your nodes to your roots. For example, I was giving an example of a house, like you split, does it have greater than 3 rooms or less than 3 rooms? Is the house in a good or bad area? And you keep splitting the trees until you sort of get to a place where your algorithm converges. So I mean, the simplest one is decision trees. And then, but decision trees is pretty good. It could be interpretable, but it has a lot of problems. So a lot of problems is that sometimes you can either underfit or overfit. So you could overfit because you don't have an optimal number of depths that your tree should build. And so you probably have, you don't know if you put more depth or or less depth. Sometimes also the number of your sort of nodes could increase, and you're not absolutely sure. And then you get into that sort of bias variance trade-off. And then that's when you start thinking about sort of the ensemble methods. And then there are mostly two of them, which is the bagging and the boosting method. And just think of the bagging as a bag, right? So bag, which means that you sort of have different little trees. So you take your data set, you randomly pick um, with replacement, and then you build different models, and then you bag them together by taking sort of the average of the predictive power of each individual bag. So, and what that does is that it actually reduces overfitting. And so random forest is one of those powerful methods. That's a bagging method. And then there's the one called boosting. So boosting, there's several types of boosting. And the idea of boosting is instead of you bagging, now you're taking a cost function, and then you're taking these trees and then you build one tree, you get a result. You use another tree to boost the performance of the first result, and then you go on until you can until it converges. And so that's boosting. Boosting, there's several types. There's sort of either boost, um, which uses some sort of mathematical equation to boost your trees. And then there's gradient boosting. In gradient boosting, you still go back to sort of building a cost function and going through an approach where you're using an update rule to update the gradient of your function. And then there's XG boost, which is the type of gradient boosting, extreme gradient boosting, where you're actually taking the same gradient boosting, but the problem with gradient boosting is that the predictive power is not very good, and sometimes it could be computationally expensive. So what XGBoost did was a sort of mathematical trick that uses something called the Taylor series to actually improve the predictive performance, and also some sort of engineering behind it to make it much more faster. And then after gradient boosting, there's light gradient boosting, LGBM from Microsoft. And then there's cat boost, where if your features are more categorical, and then you could actually do cat boost. And so the reason why I've gone through all these sort of explaining each model is that you could see that every model, they have their own strong properties, right? So they have on different use cases. So if you're trying to do something simple and you want it to be more interpretable, you could use a logistic regression or naive Bayes or something. If you're trying to use something with very powerful sort of predictive performance, you could use a random forest or an XGBoost if you don't care about interpretability. So like I mentioned, it just depends on the problem, and it depends. So for me, most times, when I'm working on a problem, I just try to use everything. So when I say everything, maybe from the non-tree based model, I might use two models, maybe logistic and naive Bayes, and then from the tree based model, I might just throw in a random forest and an XGBoost. But so far, for sort of tabular data, XGBoost is the state of the art. It's probably, so far, it's still the best algorithm out there. It's been around for a few years, but it's mostly outperforms other algorithm in terms of predictive performance. Yeah.
Wow, thank you very much. Thank you very much. Um, okay, the next question is, do we always have to scale data sets while building some models? And if so, why do we scale data sets?
I do
Is
skip.
scaling required in every model building? And why do
Oh,
we scale?
that's a good question. The answer is yes and no. Um, so the reason why I said yes and no is that this is actually the truth. You always need more data if you want good predictive performance. You want new data, because you want to sort of introduce um, new experience to your model. If I use that word loosely. So yeah, new data is always, or more data is always very. I mean, yeah, more data is very, very, very important. It's extremely, extremely important. So I can give you an example. Spotify just launched in Nigeria, right? It's one of the biggest brand. They just launched a few days ago in Nigeria, and everybody's really excited about it. They in sort of the music streaming business, they have probably one of the best set of machine learning engineers building recommendation systems. So I'll use the word loosely, Rexes. So they've been building Rexes for years, right? So, and the idea of recommendation system is to sort of recommend very good music to people, and also just try to keep them glued on the music streaming app. So let's say, for example, I could give you an example of what a cold start Rexis looks like, right? So let's say there's Sophia, Gaurav, and me. You could call us ABC. I listen to this type of music. Gaurav listen to some other type of music, and maybe Sophia listens to another type of music, right? And so you could actually put our music preference or our music choice in a matrix. So it becomes in some cases, it becomes a very large matrix. So let's say they have 5 million users with 200 million songs or whatever. You could have, that's going to be like 200 million times 5 million in a very huge matrix. I mean, now there are a lot of methods that you could do matrix factorization and sort of try to reduce it, which it's much more easier for people to do now. So that's an example of a cold start. How can you recommend music to me based on what I've listened to and based on what other people who have listened to what I've listened to have also listened to, and from there you could start building the recommendation engine, right? But now think about the data that they have is actually data from 5 million people that are non-Nigerians, maybe Nigerians in diaspora, yeah, that's fine. But people from other countries, right? So now they're just entering a new market and they're getting new data from people. It means that they probably need to get those data as a training data set and retrain their model, right? So that's an example of where scaling data set works and just getting more data set works. But also depending on the model, machine learning or deep learning, more data is better, but better data is even better. So you could have more data, but sometimes also the quality of your data set matters. So you could say you're scaling, but if you scale and the quality of the data set is still not good, maybe you won't get good results from them. So scaling is good, but scaling with sort of quality data. So doing data quality check helps. But yeah, you can never go wrong with data. So it's always important. Yeah.
All right, thank you. Okay, please, can you differentiate between model parameters and hyper parameters?
Oh, yeah. So I mean, so model parameters and model hyperparameters are they're different. So hyperparameters are actually you think of it of parameters that you put into your model. Sometimes you actually predefine what they are. I mean, sometimes you use scikit-learn, and scikit-learn comes with like default parameters. But one thing I would like to tell people is that if you're building machine learning model and you're using scikit-learn, you cannot go wrong with the documentation. So try to check documentation to see what the default hyperparameters are. So maybe if you're doing random forest or XGBoost, it will tell you the number of leaves, number of samples, number of what's the depth, and just the different, if it's a regression or a classification problem. Is it what loss function is it using and things like that. But those number of leaves and those are the hyperparameters. Those are the parameters or hyperparameters that you give the model to be able to do some certain iteration and give you back a model that you could use for prediction, right? And then the parameters are actually what the model gives you back. So if you're building a logistic regression, for example, the parameters are the weights of sort of each individual feature after it's built the model. And also you could have parameters in neural network and deep learning. Right now we are actually in machine learning. I've gotten to the stage where the number of parameters that you have, or the number of sort of trainable parameters that you have, it's very important. So I don't know if you guys have heard of, like, there's a company called OpenAI, which is a sort of non-profit in quotes. I don't think it's non-profit. It's so OpenAI is actually it's a startup started by a few people with Elon Musk, and they're trying to sort of democratize AI. So they've been releasing stuff called LLMs. So LLMs is large language models, where they've been building models with so many model parameters, billions and billions of model parameters, and they're trying to sort of build large language models that can solve problems in language and NLP, so NLP and language tasks, and can probably answer almost every question. So trying to bring some of the world's largest data. And what they've also seen is that sometimes the larger the number of parameters, which is in billions in this case, the better the data. So yeah, so the hyperparameter is what you give the model. The model parameter is what the model gives you.
Okay, thank you for that. So, okay, what is train test split, and why do we perform it on data sets?
What is a train test split? So I mean, a train test split is splitting into training and testing. So the idea of train test splits is there. In some cases, you're building a model, but you want to know how well your model is. You want to know have I done a good job or not? And that's why mostly people do train test splits. So you take 80% of your model and you can train on it, and then you probably take 20% and then you test. And the idea behind the testing is that you could use that to sort of check the predictive performance of your model. So let's say, for example, you're trying to do a regression problem, you're predicting the price of houses. So you train on some 80% of the data, and then for 20%, you test. And the reason why you test is because the 20% that you're testing on, you already know the prices of the data. You already know the prices of the houses, for example. And so you want to see what your prediction is going to give you against what the actual values are. So that's why you have predicted versus actual values. And then there are a lot of different metrics that you could use to combine both. So in the mean squared error, RMSE in regression, in classification is a little bit different. You have a whole bunch of stuff, precision, accuracy, F1 score, and all that. So it depends on the kind of model that you're using. But yeah, the train test split is you mostly splitting. How you split your data is a different thing entirely. So in most cases, we all do random splitting, because we have data that is sort of not time dependent. So if you have like your time dependent data, maybe like a time series data, you cannot do random splitting. So think about it. If you have I don't know why I keep using stock prices, which sucks. If you're predicting stock prices, which and you're trying to predict, you cannot do sort of random sampling and say you want to randomize your train and your test, right? Because let's say you have stock data from the last 5 years. Typically, what you do is that you use your first 4 years to train, and then you use your next 1 year to test. So it's sort of an idea that you do like a forward splitting, right? So you split based on time, right? So the train test split just depends on the data, and also it's very important for you to get prediction to understand sort of the predictive performance of your model. One thing I didn't mention that wasn't mentioned in the question also is sort of validation. So I've seen people do test validation, train test validation, right? So basically you take your training data, or you take your data, you split into train and test, and then you take your test, your train, you split your train into train and validation again. And the idea is because you want your validation before running your model on your test set, your validation set, you use it to check just to know that you're not overfitting or underfitting from your model. But also it also helps you when you're trying to do hyperparameter tuning. So you're trying to sort of tune some of the hyperparameters depending on the method you're using. Maybe you're putting on a grid search, you're doing a randomized search, or some sort of Bayesian hyperparameters. But yeah, it helps you. Your validation set actually really helps you. So I would say, in some cases, try to use the validation set. There are other methods you could also use, the k-fold cross validation, leave one out validation, stratified validation. So there are a lot of validation techniques you could use, but it's always very good. And then outside of the question, another thing is the trick of training and splitting. So I mean, depending on the size of the data. So I do tell people that if you have data less than 10 raised to power 4, which is the 10,000 examples, use 80/20. If you have like a million, 10 raised to power 6 number of examples, you could do a 90/10 or a 95/5. So as your data gets larger, your training examples or your splits should have more training data. So you have like a billion rows or a billion training examples. You could always split 95/5 or 98/2 because 2% of this test set is already good. Because what is 10%, 2% of a billion is already 20 million or something example. So yeah, so just know that let the percentage of your training set scale as your number of data goes up. So yeah.
Okay, so in essence, do we split our data set before scaling or we scale after splitting? Which one comes first?
Do you split your data set? I mean, already for you to think about scaling, it means that you've already split your data set. Yeah, it means that you've already split your data set, which means if your data set is already in production or you're already using it, and then you're getting more data to scale, right? So in some cases, what people do is that they check for something called data drift and model drift. If you're in production, it means you're looking at how well your model is performing when it's seeing new data, or how well are the properties of your data. So your distribution of your data changes. And then if you start seeing drift, you just take all the new data and you try to just add it to your training data set and retrain. Another thing also is that you could probably change your test data because now your new data set has some other examples, right? So you could take from it and add it to your test data set. But also it depends on the kind of training that you're doing, right? Are you sort of doing online or offline training? Are you doing some sort of batch training or batch prediction? Is it something that you're doing? You have to retrain every day. I mean, for you to do that, if you have a lot of data and you want to scale and train, I mean, you need to have the infrastructure. So you need to probably be at the Facebook, Google, Amazon level, right? Or is it something that you want to do once every 30 days, or you want to get the data, do it offline, do your batch prediction online? So there's so many strategy, and it just depends on what your computing powers are, what are your goals, how is your data, how easy for you to scale.
Okay. All right, thank you for that. What is meant by class imbalance and how can we deal with it?
Oh, okay, yeah. Class imbalance is actually one of my favorite when I just started machine learning. And also it's exciting because it's a real problem for a lot of people. So the idea of class imbalance is when you're building a classification method, you could have it in regression depending on the distribution, but you have sort of more majority class and sort of than more minority class. So, I mean, technically, you want your model to have like 50-50 minority or majority class. But in real world scenario, it's not always like that. You always have like 70-30, 80-20, and those are not even really huge class imbalance. Those are still pretty good. I mean, I've seen data set with class imbalance of like 99.9999 to 0.1 or 0.001 or whatever it is. So think about if you the classic class imbalance problem is fraud detection, right? So just think about if you work in an e-commerce space, you work for maybe Jumia or Konga, and you're trying to see people that are using some sort of like stolen credit card to order things online, or just, and you're trying to predict fraud or detect fraud ahead, and your data that you have is basically there's fraud and there's no fraud. And think about it, 99.99% of the time there are no fraud, right? And anytime you see fraud, it's actually probably the little 0.001 percentile or so. So your data is very, very highly balanced. And what it means is that when you train your model, the intelligence is actually coming from the majority. So your predictive performance is coming from the majority, right? And which means that each time it sees fraud, it's possible that it's not fraud, right? And so that's the idea around sort of class imbalance. There are certain things you could always do to help if you find yourself in that regime. And I think the most important one is the kind of metric that you use. And that's why in classification, using accuracy is always a terrible, terrible metric. So accuracy is always terrible. And the reason is that there's something called the accuracy paradox, where because of the way your accuracy is calculated, it's actually geared towards what it's predicting correctly. So if it's predicting no fraud correctly, your model is probably going to be 90-something% accurate, but that's not good. That's why when time you're building a classification model, it's always good to have other metrics, your precision, your F1, your recall. They help you in sort of understanding the predictive power of your model. That's that. And then the other thing you could do are sort of some different techniques that you could do to your data set before building your model. There are mostly two methods. Before I go to those two methods, another thing you could do in your data is segmentation, right? So data segmentation is that I have this data, maybe the people that would use a fraudulent credit card are going to sort of do a lot of transactions within the last 5 minutes. Can I sort of cut my data to looking at people that have done multiple transactions in 5 minutes, right? Can I segment my data to do that? Can I segment my data some sort of zip code? So there's just so many sort of behavioral patterns in your data. And you could only understand that when you explore your data, when you do exploratory data analysis. And with that behavioral pattern, you could do sort of data segmentation, and that would reduce the class imbalance. The other method is sort of undersampling and oversampling. So the idea of undersampling is that, let's say you have 99% to 1%. What you do is you take your majority class, which is the 99%, and you undersample. And then you have like a balanced class now. But you could probably see a problem with that because when you undersample, you would notice that the majority class, you're reducing it, and it's very possible that you're losing important information from that if you undersample. But in some cases, it probably works well. So, like I said, always no free lunch theorem in machine learning. There's no perfect method. Then the oversampling is that you're taking the minority class, the 1%, and then you're boosting it up. You're creating synthetic data. That could also be bad. So there are different type of oversampling. I'll probably go through maybe two of them. There's the random oversampling, where you're taking the 1 percentile, which is the minority class, and you're sort of randomly oversampling or creating something. There's one that I typically use a lot, which is called SMOTS. So SMOTS stands for Synthetic Minority Oversampling Technique. And the idea around SMOTS is that you have your minority class and you're trying to create a lot of samples, but instead of you doing a random undersampling, you take your data, it could be 10, 100 dimensions, you put it in a 2-dimensional space, and then from one sort of example to another example, so just think of your training example compressed in 2 dimensions, you find the nearest neighbor. So you do like a nearest neighbor, and then you draw like a straight line from one example to another. And then within that nearest neighbor, you put sort of synthetic data on it, right? And so the idea around that is that, yeah, you're doing some oversampling, but you're not randomly oversampling. You're creating synthetic data that are similar to other data based on the properties. So I've seen that work. But also the other problem you have with oversampling, maybe random or small, especially random oversampling, is that it's also very possible that because you're repeating stuff, you could be introducing a lot of noise and a lot of bias into your algorithm, right? So there are no, I mean, you cannot say, oh, this is the absolute answer. So it depends on your problem. It depends on the threshold of your majority and your minority class. And also, it just overall depends on the data you have. Yeah, that's a long explanation.
Thank you. I'm really learning a lot. Thank you so much. Okay, before we go ahead, our interns, we're still expecting more questions from you. And also, we'll be taking questions from members of the AI lab team.
Okay.
All right, so one more from me, and then we'll take from every other person. To reach my dream of machine learning expertise, what else, in addition to this machine learning extension, would you recommend that I'll need to do or to put together?
To solve the holy grail of AI, which is artificial general. To reach your goal of becoming a machine learning expert. So I think it's little incremental knowledge, right? I feel like you cannot get there in 2 months or in 2 years, or it's just very little incremental knowledge. Working on real world problems, because I know that I feel like a lot of people sort of fall into this sort of rat hole of always, it's good for start. I did it when I started, solving cargo problems, but the truth is that cargo is not a real world problem. You need to work on real world problems, real world data set, where in some cases, maybe 90% of your time, you're not even doing machine learning. You're probably just cleaning data, which is true, which is, the quality of your data set determines the quality of your model, right? So sort of doing real world problem is important. So I would say, you can learn and do stuff, but after the machine learning externship, just start applying for jobs. Just get your first job, hands-on, and then you start to understand and then create a niche for yourself. And also the reason why I said so is that there's so many things to learn that you could get overwhelming, but you don't need to be overwhelmed. And you don't need to understand everything. Well, yes, you need to understand the sort of very basics. You need to know how to code, right? But also, you need sort of this hands-on experience. So hands-on experience is very, very important. I would say it's probably more important than anything you're going to learn, because it's always good to learn by doing. And so that's important. In the machine learning world, I mean, there's some models that I'm using that were created last year. They just wrote the paper last year, 2020. And there's some models I'm going to use in the future that the scientist that's going to create the algorithm is probably still sleeping somewhere right now and hasn't even thought about it. And so it's a rapidly changing and evolving field. And you have all the time. You even get tired because there's just so much information coming out every day, right? So I would say mostly just learn by doing and then follow the trends and try to understand what's going on.
Thank you. Learn by doing and follow the trends. Thank you.
Yeah.
Okay, I'll be taking questions from our interns and the AI lab team members. I can see Precious raising his hand. Precious, please go ahead with your question.
Thank you so much for this. I have a quick one.
Okay.
My question is, with the turn of deep learning and neural networks now, like that's the thing in vogue as a data scientist or machine learning engineer, are regression techniques still valid? Are they still used or still important?
Oh yeah, of course. They're still used. I mean, there's some cases deep learning. So think about deep learning and neural networks. They've been seen to be very good with unstructured data set. So if you have images, for example, for computer vision, they're pretty good, right? Because you cannot use regression for that. And then if you have text data set, so there are a lot of NLP tasks. So text classification, machine translation, named entity recognition. I mean, there's so many things you could do with languages. So they've seen them to be really, really good. But also in those two cases, you need to sort of be working on a problem where you can do transfer learning or where you have very, very large data set, right? And so if you have small data set, deep learning is probably not going to work. You might overfit. And that's where you still come back to like the classic traditional machine learning techniques. And, for some companies, they don't even have enough data set, right? So they're still going to go back to the regression methods and use them. And then so I was talking about data set. Then another thing also is that I think I mentioned that it's not all problems that you can solve with deep learning that you scale easily. In sort of healthcare, for example, people that do clinical trials where maybe your data set is you tracking 1,000 people that has HIV for 10 years and you're trying to see their progress, right? You don't have a million or a billion record. You're still going to go back to the classic technique, not only because you don't have a lot of data, but also because anything you build in healthcare, you want it to be explainable, you want it to be interpretable. So, and interpretability in deep learning is always very difficult.
Yeah, sure. Thank you.
Precious, I hope that's clear to you.
Yeah.
Okay. Basil is also raising his hand. Basil is a member of the AI lab team.
Okay.
Basil, please go ahead with your question.
All right, thank you, Sophia. Hi, Wale. Thank you for taking your time to share your knowledge with us. So, question is, so like over the years, recurrent neural network, like it has been found to be like the state-of-the-art algorithm for sequential data, and is mostly used by the Apple Siri and Google Voice Search. So my question is, there are two types of recurrent neural networks I know, the LSTM and the gated recurrent units.
GRU and LSTM.
Yeah. So, I feel like LSTM is mostly used like the industry. So I want to understand what is it that LSTM has over GRU?
Yeah, that's a very good question. We're entering the deep learning territory. Sorry to disappoint you. RNNs are not the state of the art again. Um, that's that's how fast the field is moving. I mean, the state of the art right now actually the transformer networks. I think Google, even Siri, they already sort of deployed sort of transformer architectures and with attention. Um, some people still have RNN in production, but in deep learning, there's something called the vanishing gradient problem, and so the idea of your vanishing gradient. So if you're doing deep learning, right, you're doing sort of this gradient descent algorithm where you're taking your model or you're taking the function and then you're taking the gradient. So depending on sort of the number of input and number of parameters you have, your gradients in this case is not a sort of one-dimensional gradient. It's sort of multi-dimensional, like a Jacobian, and then you use an update through, right? But you get to a stage where the gradient just gets smaller and smaller and smaller and smaller and smaller. And then you could have like this sort of vanishing gradient problem and it affects your model. So one of the things that LSTM does is that it curbs that vanishing gradient problem. One. Then another thing also is that, so that's why they call it long-term short memory. I say long short-term memory. So which means it could, because the gradient is not vanishing, it could actually remember things back because you're working with sequential data and your idea, yeah, and basically you want to be able to remember the past of something to predict the future. And so that's what I would say LSTM has over GRU. I mean, I don't have a board, but I always actually find the sort of understanding the way LSTM works to be very fascinating. Let me see. Give me a minute. So if you go on Google and type this, just this name, I'm typing it now, and everybody should see it. Just type Christopher Ola LSTM. He has a very good tutorials on LSTM. Very, very good tutorial. And that sort of will help you understand LSTM very well. But just in summary, it's two things. It actually remembers it has better memory than GRE, which means it remembers sort of long-term stuff better. And also the vanishing gradient problem is really a huge problem when using RNN. So LSTM helps cope with that.
Yeah, thank you very much, Wale. So yeah, can you like you just said something about vanishing gradient, and can you like explain, like I've heard of exploding gradient as well.
It's
Can
the
you
same.
like tell me?
Can the difference?
Yeah, exactly. Exploding gradient and vanishing gradient.
Yeah, so mostly it's like I mentioned, the vanishing gradient is where your gradient so becomes vanishing, which means the values are getting smaller and smaller, right? And then your exploding gradient descent is where it's just exploding, it's getting bigger. So just think about just standard. I'll probably say let's think of I'm trying to find a pretty good example to use. Just calculus, right? So let's say therefore you're trying to differentiate a function and you're trying to differentiate this function for very small values of x, right? So let's say that you have like you have 1 over x, right? And let's say x is no, yeah, let's say you have 1 over x and you have the values of x, right? And let's say x is 2, right? So 1 over 2 is 0.5, right? Now, let's say that you want to start differentiating that. If you take 1 over x and you differentiate it, you have minus 1 over x squared, right? And so x squared, if x is 2, 1 over 2 squared is 0.25. If you differentiate that again, you probably have minus 2, or no, you have 2 over x cubed, right? And so which means the denominator that has x, the power continues to go up. And as the power continues to go up and you have a value for x, it means that the sort of value in the denominator becomes much smaller and it tends towards infinity, right? So which means it's, instead of it getting smaller, it's getting bigger and bigger and bigger. And that's where you see exploding gradient. And so the idea is that your gradient just gets bigger and bigger.
Yeah, that's fine. Thank you very much.
All right, you're welcome.
Wow, thank you. We can go on and on and on asking more questions.
I'm absolutely
for time's
fine.
sake, we have to call it a day for time.
Okay.
But thank you so much. Thank you so much. Before you leave, please, do you have any words for our interns? Any words of
not really. I think just, I mean, building knowledge in machine learning is incremental. You don't have to like jump the gun. Try to start little by little, and try to build, learn as much as you can. Build your portfolio. Be very thorough. So when I say very thorough, is that you're trying to build something, you're trying to use scikit-learn. Remember that sometimes anybody can go and do import scikit-learn as sklearn or whatever, import sklearn, and write 3 lines and build a model, right? What differentiates you, or what will eventually differentiate you from others, is that you actually understand whatever the scikit-learn model that you're trying to import does. You sort of understand the trade-offs. You understand why you're choosing this hyperparameter. You understand what the cost function for this is. So being very thorough and sort of understanding whatever you're doing actually helps in the long run.
Thank you so much, Wale.
Yeah, thanks for having me.
It has been an exciting, amazing, educative session with you. And we appreciate you. Thank you for coming.
Yeah, thank you so much. Yeah.
And to our interns, please keep your questions coming on Slack. We're always here to give you answers. Thank you so much, Wale. And
yeah, thanks for having me.
Handing you over to Gaurav for the closing remarks.
Yeah, sure.
It was really wonderful and insightful webinar. I express my heartfelt gratitude to Mr. Wale for guiding us through the questions. I hope all our questions and doubts, blockers have been cleared and we are ready to take off for our machine learning journey. As the saying goes, learning never stops. At Hamoye, we are continuously working to provide you the best so that you can stand out in this field. We have already started the premium courses, and those who have not yet enrolled, I would urge you to get started your machine learning journey. And those who have already done, big thumbs up to them. Once again, thanks Mr. Wale for taking out your precious time, and thank you everyone for joining today. Have a good day ahead. Thank you. Happy computing to all.
Yeah, thanks. Thanks for having me. Yeah, have a good weekend, guys.